Welcome to the Deep Dive, the show where we slice through the complexity of massive topics, extracting the absolute essentials and give you that crucial shortcut to being truly well-informed. Today we're plunging headfirst into something that, for many, still feels astonishing, almost like magic: modern artificial intelligence. Think about it, we see chatbots that can generate incredibly human-like text, carrying on conversations that feel remarkably natural, or systems that can recognize complex images with an uncanny accuracy that rivals, and sometimes even surpasses, human performance. It's captivating, certainly, and perhaps for some, a little intimidating. So what exactly is happening under the hood? What are the fundamental principles driving this AI revolution?
That's really our central mission today. We're going to pull back the curtain, not just on what these systems do, but really how they work, starting from the very simplest building blocks. We'll embark on a fascinating journey from the humble artificial neuron through how these tiny units learn to make sense of data and then build up to the sophisticated architectures like the transformers that power those large language models, the LLMs you hear so much about, like ChatGPT.
And here's the best part. You absolutely won't need a computer science degree to follow along. Our goal is to truly demystify this, giving you not just the what, but the how and the why, without getting bogged down in overwhelming jargon. We're talking surprising facts, intuitive explanations, and a clear understanding that will leave you with a real grasp of how these incredible systems operate. So if you've ever wondered about the nuts and bolts of AI, this is your deep dive. Let's unpack this, starting with the very smallest component.
Precisely. Okay, so at the heart of every artificial intelligence system, well, specifically neural networks, you find what's called an artificial neuron. Now, it's crucial to understand. While the name is loosely inspired by biological neurons in the brain, an artificial neuron is fundamentally a computational concept. It's not attempting to perfectly simulate human brain cells. Not really. In its simplest form, it's just a unit that holds a single number, specifically a number between 0 and 1. We refer to this number as its activation. You can visualize it as the neuron lighting up when its activation is a high number, closer to 1, signifying it's highly active, and being dim or inactive when it's closer to 0. It's a bit like a tiny light bulb that can glow at varying intensities.
Okay, so a single neuron is just a number, a light bulb that glows. But that doesn't sound very intelligent on its own. I mean, how do these numbers, these individual light bulbs, combine to do something truly intelligent? Like recognize a handwritten digit, which I know is a classic benchmark in AI. How do they get organized to perform such a task?
Yeah, that's where the concept of a neural network comes in, organized into layers. Let's take that classic example you mentioned. Training a network to recognize handwritten digits, like the famous MNIST database, which is a collection of tens of thousands of these handwritten digits. Imagine a scanned image of a digit, say your handwritten 3-font. This image is typically a grid of pixels, perhaps 28 by 28 in size, in grayscale.
Okay, 28 by 28 pixels, that's 784 individual pixels. I can see how each pixel could be represented by one of our artificial neurons, right?
Exactly. Each one of those 784 pixels corresponds directly to one artificial neuron in what we call the input layer. The activation of each of these 784 neurons will represent the grayscale value of its corresponding pixel. For instance, a pixel that's completely black would have an activation of 0, and a pure white pixel would have an activation of 1. Shades of gray would fall somewhere in between. So when you feed an image of a handwritten digit into the network, it literally lights up a specific pattern of these 784 input neurons.
Right. And then at the other end of the network, we have the output layer. For this handwritten digit task, that layer usually consists of 10 neurons. Each of these 10 neurons represents one of the digits, from 0 to 9. The activation of these neurons, again, a number between 0 and 1, tells the system how strongly it believes the input image corresponds to that particular digit. So when the network has made its prediction, the neuron in this output layer with the highest activation, the brightest one, is its choice, its best guess.
But the real magic happens in between. Connecting the input layer to the output layer are what we call hidden layers. For a long time, especially in the early days, these hidden layers felt like a giant question mark, even to researchers. We knew they were essential, but their internal workings weren't immediately obvious, almost like a black box. In our simple handwritten digit example, we might have, say, 2 hidden layers, perhaps with 16 neurons in each. The actual number of hidden layers and the number of neurons within each layer isn't fixed. It's often a design choice determined through experimentation to achieve the best performance. And these layers are where the network learns to extract increasingly abstract features from the raw pixel data.
Abstract features. Like what?
Well, for instance, the first hidden layer might learn to detect simple things, like edges or corners in the image. Then a subsequent layer might combine those edges to recognize more complex shapes, like loops or horizontal lines, which are crucial for distinguishing between digits like, say, a 3 and an 8.
Okay, so we have these layers of neurons, each holding a number, a brightness value. The core of the network's processing power really lies in how the activations in one layer actually determine the activations in the next. It's this intricate flow of information, almost like a domino effect, right, that allows the network to transform raw input into a meaningful prediction.
It is. The mechanism is quite elegant, but incredibly powerful. Each connection between a neuron in one layer and a neuron in the next layer has an associated number called a weight. Think of these weights as strengths of connections, or perhaps better yet, as finely tuned dials and knobs. When a neuron in a subsequent layer calculates its activation, it does so by computing a weighted sum of all the activations from the neurons in the previous layer that are connected to it. If a weight is positive and strong, it means that previous neuron's activation will contribute significantly to activating the next neuron. If it's negative, it will inhibit it, pushing the next neuron's activation down. This lets the network learn which inputs are important and which should be, well, ignored or suppressed.
So we're multiplying the previous neuron's brightness by this weight, this dial setting, and summing them all up. But is there anything else? Does a neuron have its own sort of baseline tendency apart from just the weighted sum of its inputs?
Absolutely, that's a great point. Beyond the weighted sum, each neuron also has an additional number added to this sum, which we call a bias. You can imagine the bias as an offset or an inherent tendency for that neuron to be active or inactive, regardless of the inputs it receives from the previous layer. It's like giving a neuron a slight predisposition to fire, or maybe to remain silent, almost like a personal threshold it needs to cross. It allows the neuron to activate even if the weighted sum of its inputs is low, or to stay inactive even if the sum is positive, but maybe not quite strong enough.
Okay, so we calculate this weighted sum, we add the bias, but the result could be any number, right? Positive, negative, big, small. But we said our neuron's activation needs to be a number between 0 and 1. How do we make sure it stays in that range?
That's where we apply an activation function. Sometimes people informally call it a squishification function to this sum. Historically, a very popular choice was the sigmoid function. This function takes any real number and elegantly compresses it into the 0-1 range. Very negative inputs become close to 0, very positive inputs become close to 1, and it provides a smooth, gradual increase in between. It effectively determines whether a neuron fires and how strongly.
But interestingly, while sigmoid was historically prominent, modern neural networks often prefer something simpler, right? Called ReLU, or rectified linear unit. Why the shift? What's so good about ReLU?
Great question. ReLU is indeed very straightforward. If the input to it is positive, it just outputs that input directly. If the input is 0 or negative, it simply outputs 0. It's like an on-off switch that only passes along a signal if it's positive. The reason for its popularity is, well, a couple things. First, it's computationally very cheap to calculate compared to sigmoid, which involves exponentials, much faster. Second, and perhaps more importantly, it helps alleviate a problem called the vanishing gradient, which could happen in deep networks using sigmoid. This made them very hard to train. ReLU keeps the gradients healthy, allowing information to flow effectively through many layers during the learning process. So this simple change from sigmoid to ReLU was actually one of those subtle but really profound breakthroughs that allowed us to train much deeper and more powerful networks.
It's really amazing to think that even at this basic level, these seemingly simple math operations, weighted sums, biases, these activation functions repeated billions of times, allow the network to pick up on incredibly subtle patterns. Patterns no human could possibly handcode. It's the first real hint of emergent intelligence we're seeing. And when you think about our handwritten digit example, with 784 input neurons, 2 hidden layers of 16 neurons each, and 10 output neurons, that adds up to a lot of adjustable parameters.
It really does. If you actually do the math, that seemingly simple structure amounts to almost exactly 13,000 total weights and biases. That's 13,000 knobs and dials that collectively determine the network's behavior. The entire network, in essence, is one crazy complicated function that takes in 784 numbers, the pixel values, and outputs 10 numbers, the probabilities for each digit. Imagine trying to manually adjust those 13,000 knobs by hand to get it to recognize digits. You'd be there forever.
Absolutely impossible.
Yeah, the structure is fixed. But the real magic, what allows these networks to become intelligent, lies in how those thousands of dials and knobs are set, how they're tuned to make the network perform its task well. And this brings us to the crucial question: how do these networks actually learn?
Right. If a human can't tune 13,000 knobs, how does the network discover the best settings itself? How does it even know if it's getting better?
That's where the concept of learning in AI really comes into play. Learning means finding the optimal settings for all those weights and biases to improve performance on the given training data. And to know if it's improving, we use something called a cost function. Think of it as a mathematical way to measure how lousy the network's current performance is. For a single training example, say, that image of a handwritten 3 that the network maybe incorrectly predicts as an 8 prints, the cost function calculates the difference between what the network outputs for each of its 10 output neurons and what you wanted it to output.
Ah, okay. So for that 3 that the network thinks is an 8, the cost function would heavily penalize it for outputting a high value for 8 and a low value for 3.
Precisely. It typically sums the squares of those differences for each output neuron. A small sum means the network is doing well on that specific example. A large sum means it's making a big mistake. Then, to get the overall cost for the entire network, you average this individual cost over tens of thousands of training examples. For the M&S database, you'd average the cost across all those images. So you end up with a single number that represents the network's overall lousiness, or error, derived from thousands of inputs, all those weights and biases. The network's ultimate goal: minimize this single cost number, get it as low as possible.
Okay, so now you know how lousy the network is. You have this number, but you need a way to tell it how to adjust all those thousands of weights and biases to get less lousy. And this is where it feels less like sci-fi and, as you said, maybe more like a really, really complex calculus exercise. We're talking about gradient descent, right?
Exactly. Imagine that cost function, which depends on all 13,000 parameters, as a complex, multidimensional surface, like a vast, crinkled landscape with hills and valleys. Our goal is to find the lowest point in a valley, which represents the minimum possible cost, the best performance. Gradient descent is an iterative process, much like a ball rolling down a hill. At any given point on this surface, the network computes the gradient.
And what exactly is the gradient in this context? Is it just the slope?
It's a bit more than just the slope. The gradient is essentially a vector, a list of numbers, one for each weight and bias, that points in the direction of the steepest descent, the direction that would make the cost increase most quickly. So to decrease the cost, what do? You take a small step in the negative direction of this gradient. You go opposite to the steepest uphill direction. Effectively, you're moving downhill towards a lower cost.
Okay, that makes sense. Go downhill.
And what's fascinating here is that the length or magnitude of this gradient vector tells you how steep the slope is at that point. If the gradient is large, you're on a steep slope, and a small step can make a big difference. If it's small, you're near a flatter area, or maybe a minimum. And crucially, the individual components of that gradient vector tell you which specific weights and biases have the most bang for your buck in reducing the cost. An adjustment to one weight might have a much greater impact on the cost than an adjustment to another. The gradient tells you which knobs to turn and how much to get the biggest reduction in lousiness.
It's worth mentioning, though, just like a physical ball rolling down a hill, there can be multiple valleys, right? These local minima on the cost surface. So the network might not always find the absolute lowest point, the global minimum. It might just settle in a pretty good valley nearby.
That's absolutely correct. It will converge towards a good local minimum, and in practice, these often perform remarkably well, sometimes even as well as the global minimum might.
Okay, so gradient descent tells us which way is down. But calculating that gradient, that direction, for thousands or even billions of parameters, that sounds computationally intense. How is that done efficiently?
That's where the real workhorse algorithm comes in. It's called backpropagation. Backpropagation is the algorithm that actually calculates this incredibly complex gradient efficiently for all those thousands or millions of weights and biases. Let's try to walk through it intuitively. Imagine our network is shown a single training example, like that image of a handwritten 2. The network first feeds forward the pixel data, activating neurons layer by layer to produce an output, a set of activations for the 10 output neurons. Let's say it's not well trained yet. Maybe it outputs a high activation for 7 and a low one for 2. Clearly wrong.
Right, so we have an incorrect output. How does backpropagation use that specific error to figure out what adjustments are needed? Like all the way back through the layers, how does the error message get back?
Okay, so the backpropagation algorithm kicks in right there. By comparing this output, high 7, low 2, to the desired output, low 7, high 2, it first determines desired nudges for the output layer's activations. For instance, the 2 neuron needs to be nudged up significantly, and the 7 neuron needs to be nudged down. The size of the nudge is proportional to how far off the current value is from its target.
Okay, makes sense for the last layer, but then how does it go backwards?
Now, here's the backwards part. These desired nudges for the output layer are then propagated backwards through the network layers. Each neuron in a preceding layer receives aggregated desires or error signals from all the neurons it connects to in the next layer. This aggregation is proportional to the connecting weights, how strong the connection was, and how much each subsequent neuron needs to change. It's like a message flowing back through the network, telling each connection in each neuron exactly how it needs to adjust its own behavior to help reduce the error observed right at the output.
That sounds almost biological, like pathways being reinforced or weakened based on the outcome.
It's remarkably reminiscent of a powerful theory in neuroscience called Hebbian theory, often summed up as neurons that fire together wire together. In artificial neural networks, the biggest increases to weights, the strongest strengthening of connections, happens between neurons that are highly active and are connected to neurons that are desired to become more active to correct an error. It's all about reinforcing the connections that lead to correct activations and weakening those that lead to incorrect ones.
And for listeners who might remember their calculus, I hear backpropagation cleverly uses the chain rule. Can you explain what that means in this context, maybe without getting lost in the equations?
Sure. Think of it like this. You want to know how much a tiny tweak to a specific weight, maybe way back in an early layer, affects the final error at the very end of the network. The chain rule lets you unravel that influence step by step through all the intermediate calculations. It tracks how a change in that weight influences a neuron's weighted sum, which then influences its activation, which then influences the input to the next layer, and so on, all the way until you see how it affects the final cost function. By multiplying together all these individual sensitivities, these little local effects, backpropagation efficiently calculates the overall impact of that single weight on the final error. It allows the system to assign blame or credit to every single parameter in the network, even ones buried deep inside, for how much it contributed to the overall error. It's mathematically quite elegant.
Now, calculating this precise gradient for every single training example at once, especially if you have millions or billions, that would still be computationally way too slow, right? Even with backpropagation.
Absolutely. It's computationally infeasible for large data sets. So to make it practical, we use a technique called stochastic gradient descent, or SGD.
Stochastic meaning
Right.
random.
Sort of. Instead of using all the training data for one massive, precise step downhill, the data is randomly shuffled and divided into small subsets called mini-batches, maybe 100 examples each or a few thousand. The network computes the gradient and takes a small downhill step based only on that mini-batch. Now, this gradient isn't the exact gradient for the entire data set, so it's not the most precise direction downhill, but it's a very good approximation, and it offers a massive computational speedup because you're processing much less data per step.
I've heard this likened to a drunk man stumbling aimlessly down a hill but taking quick steps, rather than a carefully calculating man taking slow, precise steps. What's the advantage of that slightly drunk, noisy approach?
That analogy is quite apt, actually. While it might seem less precise, this constant, slightly noisy but very quick adjustment allows the network to converge toward a good solution much, much faster. And there's another benefit. It also helps the network avoid getting stuck in those minor valleys or local minima on the cost surface. Because the gradient estimate from each mini-batch is a bit different, it introduces a bit of randomness. This noise can effectively kick the optimization process out of shallow depressions and help it explore the landscape better, potentially finding deeper, better minima. So it's not just about speed, but also about robustness in finding a good solution.
Okay, so let me try to sum up this fundamental learning process. We have backpropagation, which efficiently calculates how much each weight and bias contributes to the overall error. Then we use gradient descent, usually the stochastic version with mini batches, to iteratively adjust those weights and biases in the direction that reduces the error. And this whole process relies on vast amounts of labeled training data, like the MICE database, where humans already labeled each digit 0 through 9 to guide the network. It's how raw data gets transformed into a system that can actually make intelligent decisions, like recognizing those digits.
That's a fantastic summary. It lays the foundation for how networks learn from labeled data. But now, let's make the leap to something truly groundbreaking in recent AI history. Transformers. Before about 2017, the world of language models trying to understand and generate human language, was largely dominated by different kinds of architectures, mainly recurrent neural networks, or RNNs, and sometimes convolutional neural networks, CNNs. While these were impressive for their time, they had some pretty significant inherent limitations, especially when it came to really grasping the nuances of human language.
What were those limitations, especially for language? I know CNNs are great for images, identifying patterns, but RNNs process things sequentially, right? Word by word.
Exactly. RNNs process text sequentially, one word or token at a time from start to finish. Imagine reading a long sentence, or even a paragraph, word by word, trying to keep track of every single preceding word to understand the current one. It's hard for humans, and it was hard for RNNs. This sequential nature severely hindered parallelization. You couldn't easily process large chunks of text simultaneously on modern computer hardware like GPUs, which absolutely thrive on parallel computations. It also made learning long-range dependencies incredibly difficult. If a pronoun like it appears much later in a text and its meaning depends on a noun from way back at the beginning, an RNN would often struggle to remember that far back. The signal would get diluted over time. It's like trying to remember the first word of a long book by the time you reach the last page.
Right, the memory fades. And CNNs, how do they apply to language if they're about local patterns, like in images?
Well, people tried applying CNNs to language by looking for local patterns too, like short phrases or n-grams, sequences of n-words. But language meaning often depends on non-local relationships. A verb might relate to a noun that's very far away in the sentence, or the sentiment of a whole paragraph could be flipped by a single word near the end. CNNs, with their focus on fixed-size local windows, struggle to capture these broader non-local dependencies efficiently. Their core strength just wasn't well suited for the flexible long-range connections common in language.
Okay, so RNNs were slow and forgot things. CNNs were too local. Then came the game changer. That 2017 paper with the unforgettable title, Attention is All You Need. This introduced the transformer architecture, which, as I understand it, radically departed from these previous models. It completely ditched recurrence and convolutions in its main structure, relying solely on a mechanism called attention. That sounds like a really bold move.
It was absolutely revolutionary, because it made transformers significantly more parallelizable and therefore much, much faster to train than any previous models for sequence tasks. This efficiency was the absolute key to scaling up. It unlocked the ability to train models on vastly more data and with vastly more parameters, leading directly to the current wave of AI we're experiencing. Think state-of-the-art results in machine translation, text summarization, and of course those huge large language models. Unlike RNNs that read text word by word, transformers kind of soak in all the text at once, processing every word in parallel. And then, crucially, they let those words talk to each other, using this attention mechanism to figure out their context.
Okay, but before any of this complex thinking or talking can even happen inside the transformer, human language words, sentences needs to be converted into a numerical format that the network can actually crunch. This is where tokens and embeddings come in, right?
Precisely. First step. Language is broken down into tokens. These are the basic units of text the model works with. They can be whole words like deep or dive, but often they're pieces of words like ing from diving, or even punctuation marks like a comma or a period. The model builds up a large vocabulary of these common tokens.
Okay, so text becomes a sequence of these tokens. Then what?
Then, each of these unique tokens is associated with a high-dimensional vector. That's just a fancy way of saying a long list of numbers. These vectors are called embeddings. So the token for deep gets its own unique list of numbers, and the token for dive gets another. You can think of these embeddings as the coordinates of tokens in a vast, abstract numerical space. And when we say high-dimensional, we mean it. In models like GPT-3, these vectors, these lists of numbers, can have as many as 12,288 dimensions, or numbers each.
12,000 numbers just to represent one word or piece of word.
Wow. But what's the point? Why such huge vectors? Does the position in this space mean anything? Yes, that's where it gets really interesting and kind of mind-bending. Directions within this high-dimensional embedding space actually start to correspond with semantic meaning. For starters, words with similar meanings tend to cluster together in this space. If you were to look at the embeddings closest to the embedding for tower, you'd likely find vectors for words like skyscraper, minaret, or spire, things that all give off a similar tall construction building vibe. The model learns conceptual closeness.
Okay, similar words are near each other. But I've heard about even more fascinating relationships, like those famous vector math examples.
Ah, yes, the classic one is king man plus woman. You take the embedding vector for king, mathematically subtract the vector that represents man, and then add the vector that represents woman. The resulting vector lands remarkably close to the embedding vector for queen. It's as if the model learns that there's a specific direction, a specific pattern of numbers in those 12,288 dimensions that corresponds to the concept of gender.
That's incredible. It's learning abstract relationships just from processing text. Are there other examples?
There are many. Some models show things like if you take the embedding of Italy, subtract Germany, and then add sushi, you end up very close to the vector for bratwurst. It's almost like the model learns directions associated with concepts like nationality and their typical foods. This super high dimensionality, like GPT-3's 12,288 dimensions, is crucial because it provides enough room to encode countless distinct ideas, relationships, and nuances without having them all interfere with each other. It's like having a gigantic library where every single concept gets its own precise, unique shelf location defined by these numbers.
So words become these points in a vast conceptual space, represented by these long lists of numbers. But what you said, transformers process text in parallel all at once, how do they know the order of words? Surely dog bites man is different from man bites dog, even though they use the same word embeddings.
That's a critical detail, you're right, because transformers process text in parallel. They don't have an inherent sense of sequence like RNNs did. So we need to explicitly add information about the position of each token in the original input sequence. This is done through positional encoding. Essentially, a special numerical pattern, another vector, is generated based purely on the token's position, first word, second word, etc., and this positional vector is added to the token's embedding vector. This way, the final embedding that goes into the model contains information about both the word itself and its location in the sentence. This allows the model to understand grammar, syntax, and meaning that depends on word order, like distinguishing dog bites man from man bites dog.
Okay, so now we have our language converted into these context-free numerical embeddings, which also carry positional information. The next big challenge, then, is to infuse them with contextual meaning. Like you said, a word like mole can mean different things: an animal, a chemistry unit, a skin growth. The initial embedding for mole is generic. The model needs a mechanism to update that generic embedding so it becomes context-specific, so that the embedding for creature in the phrase fluffy blue creature actually reflects a fluffy blue creature, not just any old creature. This must be where that attention mechanism really comes into its own.
Exactly. This brings us right to the heart of the transformer, the attention mechanism. This is what allows words to essentially talk to each other and refine their meanings based on the surrounding context. It's like each word looks at every other word in the sentence or sequence and decides how much attention to pay to each one to fully understand itself in that specific context. At its core, a single unit of attention, often called an attention head, is defined by three learned matrices. These are just big grids of numbers, parameters that the model learns during training. These are the query Q, key K, and value V matrices. Query, key, and value. Okay, those names sound a bit like looking something up in a database. Can you break down what each one does? That database analogy is actually pretty good. Think of the query Q matrix this way. Each word uses it to generate a query vector. This query vector is like the word asking a question about the context. For example, the noun creature might generate a query vector that effectively asks, are there any adjectives preceding me in this sentence that describe me? Or maybe a verb like ran generates a query asking who or what is the subject performing this action. The query vector is a high-dimensional list of numbers representing this question.
Okay, so each word formulates a question using the Q matrix. How do other words answer these questions?
Simultaneously, every other word in the sequence uses its own learned key K matrix to generate a key K vector. You can think of these key vectors as providing the potential answers to the queries. So for our creature example, adjectives like fluffy or blue would generate key vectors that essentially say, yes, I am an adjective and I am in this position relative to you. Both the query vectors and the key vectors usually live in the same, somewhat smaller dimensional space, which allows us to compare them directly to see how well they match.
And how is that match measured? How does the word know how relevant another word's answer is to its question?
The system measures relevance by computing the dot product between a word's query vector and every other word's key vector in the sequence. The dot product is just a mathematical operation that gives a single number indicating how well two vectors align. A larger dot product means a stronger alignment. The key is highly relevant to the query. You can visualize this maybe as grid, where each cell represents the dot product between word I's query and word J is key. Brighter cells, or bigger dots, mean stronger relevance. In the lingo, when a key aligns strongly with a query, we say that the key's word attends to the querying word.
Okay, so we get these raw scores, these dot products indicating relevance, but they could be any number, right? How do they become useful attention weights?
Right, those raw dot product scores can be any real number, positive or negative. To turn them into something more useful, like a set of weights that tell us how much attention to pay, the network applies the softmax function to these scores. Softmax does two things. It makes all the scores positive, and it makes them sum up to 1 for each querying word. So it converts the raw relevance scores into a probability distribution. This resulting distribution is the attention pattern, a set of weights, all between 0 and 1, showing how much each word in the input should influence the understanding of the querying word. A large weight means pay a lot of attention. A tiny weight means ignore this word. This attention pattern isn't just a byproduct, it's the model explicitly figuring out, okay, to understand this word here, these other words are the most important context. It's like how your brain focuses on key phrases when reading.
And I recall there's a crucial detail here, especially for models that generate text, like predicting the next word. It involves something called masking or causal attention. Why is that needed? What's this autoregressive property it preserves?
That's a vital point, yes. During training, especially for models designed to generate text step by step, like chatbots, we absolutely need to prevent the model from cheating. It shouldn't be allowed to look ahead at the words it's supposed to be predicting. So attention is masked. Before applying the softmax function, any dot products that correspond to a word attending to a word that comes later in the sequence are artificially set to a very large negative number, like negative infinity. After softmax, these large negative numbers become effectively 0. This ensures that a word can only attend to words that came before it, or itself, in the sequence. This preserves the model's autoregressive property, meaning it generates output one step at a time, where each step depends only on the previous steps it has already generated or seen in the input. Without masking, the model would just learn to copy the next word, not how to predict it based on context.
That makes sense. Prevent cheating by hiding the future.
Exactly. And it's worth noting a computational bottleneck here. The size of this attention calculation, comparing every word to every other word, grows quadratically with the length of the input sequence. If you double the length of the text, the number of dot products you need to compute becomes 4 times larger. This quadratic scaling is a major reason why handling very long texts, long context windows, is computationally expensive for standard transformers, and it's an active area of research to find more efficient attention mechanisms.
Okay, so the model has calculated this attention pattern, these weights, indicating which words are relevant to which. Now, how does it actually use this information to update the word embeddings and make them context aware? This is where the value V matrix comes in, I assume.
Precisely. Each word's original embedding plus positional encoding is also multiplied by its own learned value V matrix to produce a value vector. You can think of this value vector as containing the actual information or meaning that a word has to offer to other words if it's deemed relevant by the query key comparison.
Yeah.
This value vector usually lives in the same high-dimensional space as the original embeddings.
So we have the attention weights saying how much to listen to each word, and the value vectors saying what each word has to say. How do they combine for the final update?
To get the final, contextually refined embedding for a specific word, the network calculates a weighted sum of the value vectors from all words in the sequence. The weights used in this sum are precisely the attention weights calculated via softmax from the query key interactions. So for our example word creature, it would take a large fraction of the value vector from fluffy, because it had a high attention score, a large fraction of the value vector from blue, and maybe only tiny fractions of the value vectors from other, less relevant words in the sentence. This weighted sum produces a single change vector, representing the aggregated contextual information relevant to creature. This change vector is then simply added to the word's original embedding. The result is a new, refined embedding for creature that now fully incorporates the meaning absorbed from its context. It's no longer generic creature, but specifically fluffy blue creature. And this entire sophisticated process happens in parallel for every single word in the sequence, producing a full set of contextually richer embeddings simultaneously.
That's a really clever way to blend information based on relevance, but what you've described sounds like a single pass, a single attention head. I know that a full attention lock inside a transformer uses multi-headed attention, sometimes dozens or even nearly 100 heads, like in GPT-3's 96 heads per block. Why so many? What's the benefit of running this process many times in parallel?
That's a fantastic question, and it's where the real power of attention truly multiplies. Running multiple attention heads in parallel is crucial, because it allows the model to learn and focus on many different types of contextual relationships simultaneously. Think of it like having a team of specialized analysts looking at the same sentence. Each head has its own separate set of Q, K, and V matrices that it learns independently. One head might learn to become really good at identifying grammatical structures, like figuring out which verb connects to which subject, even if they are far apart. Another head might specialize in recognizing how adjectives modify nouns. Yet another might learn more abstract semantic relationships, maybe picking up on the fact that Harry and wizard in the same context strongly suggests Harry Potter, whereas Queen, Sussex, and William in the context of Harry might point to a completely different Harry, the prince.
Ah, okay. So each head develops its own expertise, offering a different perspective on how the words in the sentence relate to each other.
Precisely. Each of these heads calculates its own attention pattern and proposes its own unique change vector to add to the original embedding based on its specific focus or specialization. Then the outputs, the change vectors, from all these different heads are typically concatenated or summed together and often pass through another linear transformation. This combined information is then added to the original embedding. This creates an even richer, more nuanced contextual representation of each word, allowing the model to integrate diverse perspectives on its meaning and relationships within the sentence. It's how the model can understand that bank in riverbank should end up with a very different final embedding than bank in savings bank, because different attention heads will focus on different contextual clues, river versus savings.
And the beauty is, all these heads can run their calculations at the same time.
Exactly.
The power of attention, and a major reason for the transformer's success, lies in its extreme parallelizability. All these complex calculations for queries, keys, values, dot products, softmax, and weighted sums for all heads can be performed simultaneously on specialized hardware like GPUs. This massive parallel processing makes training these models incredibly efficient compared to the sequential nature of RNNs. This efficiency has been absolutely key in allowing deep learning models to scale to unprecedented sizes. And scale, as we're seeing, often leads to significant qualitative improvements in performance. Just to give you a sense of the scale, in a model like GPT-3, it's estimated that nearly 58 billion parameters are devoted just to these attention mechanisms.
Wow, 58 billion parameters just for attention, just for figuring out how words relate to each other in context. That's staggering. Now, while attention handles this intricate dance of contextual meaning, refining those word embeddings, I understand there's another major component working alongside it in the transformer architecture, the multi-layer perceptrons, or MLPs. Sometimes they're just called feed-forward networks. What's their role in the grand scheme?
Right. Well, attention is all about words dynamically talking to each other to understand the current context. The MLPs provide the extra capacity to store facts, or general knowledge, that the model learns during its vast training process. These MLP blocks are typically interleaved with the attention blocks. After attention is refined the embeddings based on context, the embeddings are passed through an MLP block. You can think of the MLPs as the network's distributed knowledge base. They don't just store generic facts. They learn to encode highly specific associations and patterns that are discovered across the trillions of words seen during training.
So, if attention is about making sense of the immediate sentence or paragraph, MLPs are where the model perhaps consolidates that understanding with its broader knowledge of the world, facts, and common relationships.
That's a very good way to put it. The computation within an MLP block is actually relatively simple compared to the complexity of multi-head attention, but it's incredibly effective. It essentially boils down to applying a couple of linear transformations, matrix multiplications, often referred to conceptually as an up projection to a much larger dimension, and then a down projection back to the original embedding dimension with a nonlinear activation function like ReLU applied in the middle, in that larger hidden space. Imagine these matrix multiplications as complex blenders. They take in the context-rich embeddings from the attention layer and then remix the information, forcing different features and concepts represented in the vector to interact. This mixing in a larger space allows the network to solidify abstract concepts and store specific factual associations within its parameters.
Can you give an example? Like, how might an MLP store a fact?
Well, researchers looking into model interpretability have found evidence suggesting that factual associations seem to reside heavily within these MLP layers. For example, if the model processes the phrase, "Michael Jordan plays," the attention mechanism helps understand the words in context. Then, when the embedding for Jordan passes through an MLP, specific neurons or patterns within that MLP might activate strongly because they've learned to recognize the concept Michael Jordan. Then, the down projection part of the MLP might be wired such that activating these Michael Jordan neurons causes a basketball direction or feature to be added strongly to the output embedding. Effectively, the MLP encodes the fact Michael Jordan is associated with basketball.
So the MLP neurons can act almost like feature detectors or even like AND gates. Like if features corresponding to Michael and Jordan are present, then activate the basketball association.
That's a useful conceptual model, yes. The neurons in that larger intermediate layer of the MLP can learn to detect combinations of features present in the input embedding. And it's worth noting that these MLPs constitute the majority of parameters in most large language models. For example, in GPT-3, estimates suggest around 116 billion parameters, roughly two-thirds of the total 175 billion, are dedicated to these MLP blocks. This really underscores their importance as the primary knowledge repositories within the network.
Okay, so we have attention for context, MLPs for knowledge. But what makes these models truly powerful is the concept of depth and scale. The data doesn't just flow through one attention block and one MLP block. Instead, it repeatedly flows through many layers of these alternating attention and MLP blocks. You mentioned GPT-3 has 96 such layers. What happens as information goes deeper and deeper through so many layers?
This multi-layered structure, this depth, is absolutely critical. It allows the embeddings to progressively soak up more and more nuanced contextual meaning and higher-level, more abstract ideas. As the information passes through the initial layers, the model might focus on basic syntax and local context. As it goes deeper, through more attention and MLP blocks, the network can start to encode increasingly sophisticated concepts, maybe things like the overall sentiment of a document, the tone of the author, the logical structure of an argument, or even underlying scientific principles related to the text. The hope, and what seems to happen in practice, is that the further down the network you go, the more abstract and rich the meaning encoded in each embedding becomes. This repeated refinement through alternating contextual processing, attention, and knowledge consolidation, MLPs, is what leads to the really impressive reasoning generation capabilities we see. And of course, this deep layered structure is a major contributor to the massive overall parameter counts, like GPT-3's 175 billion total parameters.
Now, a vital structural detail that actually enables the training of such incredibly deep networks, I hear, are things called residual connections. You mentioned them briefly. How do they work and what problem do they solve? Why are they so crucial for deep networks?
All right, residual connections or skip connections are deceptively simple but profoundly important. They were a key innovation that unlocked the ability to train very deep networks effectively. Essentially, a residual connection allows the signal to bypass a sublayer, like an attention block or an MLP block. The original input to the sublayer is added directly to the output of that sublayer, typically before a normalization step. Their genius lies in solving the vanishing gradient problem, which plagued early attempts at training very deep networks. Without residual connections, as the error signal, the gradient, backpropagated through many, many layers, it could become extremely small, effectively shrinking towards zero.
So the early layers wouldn't get a strong enough signal to learn.
Exactly. The gradients would vanish, and the early layers would essentially stop learning. Residual connections create a kind of information highway that allows the gradient signal to flow much more directly back through the layers, bypassing transformations that might diminish it. This ensures that even the earliest layers receive a meaningful error signal, allowing the entire deep network to train successfully. It's like having a direct line of communication that prevents the crucial learning message from getting lost or diluted across dozens or hundreds of layers.
Okay, this is all building up a picture of incredible complexity and scale. But here's where it gets perhaps even more mind-bending, connecting back to some cutting-edge research trying to understand how these models actually store all this information. The superposition hypothesis. It sounds counterintuitive. We think of dimensions, like 3D space, having 3 perpendicular directions. If you have an n-dimensional space, you can fit n perfectly perpendicular directions, right? Each representing a distinct idea. But superposition suggests something different.
It does. The standard geometric intuition breaks down a bit in very high dimensions. The superposition hypothesis suggests that if you relax the constraint from needing perfectly perpendicular orthogonal vectors to represent distinct features or ideas, and instead allow nearly perpendicular vectors, say, vectors that are maybe between 88 and 92 degrees apart instead of exactly 90, then you can fit exponentially more distinct concepts into the space than there are literal dimensions. For example, in a relatively modest 100-dimensional space, you might be able to comfortably fit and distinguish hundreds of thousands of distinct nearly perpendicular vectors, each representing a different idea or feature. Now scale that up to GPT-3's 12,288 dimensions. The number of potential concepts it could theoretically represent in this superposed way becomes absolutely astronomical.
So what does this mean practically? Does it imply that individual neurons or directions within the network's high-dimensional spaces might not represent just one single, clean feature, but rather a combination of many features simultaneously?
Precisely. A single dimension, or a single neuron's activation in an MLP, might be involved in representing multiple different concepts or features, which are encoded as directions that are not perfectly orthogonal, but distinct enough for the network to use. This hidden capacity provided by superposition in high-dimensional spaces might partially explain why these models perform surprisingly well. As they scale up, they seem to be learning and storing far more information than their raw parameter count might initially suggest. It also helps explain why they are so incredibly hard for us humans to interpret. You often can't just point to one neuron and say, that's the cat neuron, or that's the Michael Jordan neuron. That concept is likely distributed across many dimensions and tangled with other concepts in this superposed representation. It's like the model finds incredibly efficient, though opaque to us, ways to pack information into its parameters.
And it's crucial to remember that all these sophisticated behaviors, these learned facts, the contextual understanding, even maybe these superposed features, they are all emergent phenomena. They arise organically from the massive training process itself, right? No human explicitly programs these detailed associations or tells the model, store the concept of king minus man plus woman equals queen. It just happens.
Exactly. These capabilities emerge from the model, repeatedly refining those billions of parameters using backpropagation and gradient descent, driven solely by the objective of predicting the next word, or performing some other task, on trillions of examples of text or other data. This training process typically involves at least two main stages. First, there's pre-training. This is where the model learns general knowledge about language, facts about the world, common sense reasoning, etc., usually by just trying to autocomplete massive amounts of text scraped from the internet. It learns by predicting the next word over and over again on a colossal dataset. Then, often comes fine-tuning. This is where the pre-trained model might be further trained on a more specific dataset or task. For models like chatbots, this often involves techniques like reinforcement learning with human feedback, or RLHF. Humans rate the model's responses, providing feedback that guides the model to be more helpful, truthful, and harmless in its interactions.
And this whole process is enabled by two key things we discussed. The ability to learn from unlabeled text during pre-training, just predict the next word, no human labels needed for most of it, and the incredible parallelizability of the transformer architecture itself. That combination allowed models to consume and learn from amounts of text that would literally take a human thousands of years to read.
Absolutely. Those two factors, unsupervised learning at scale and parallel computation, were the magic ingredients. And the power of the transformer architecture also lies in its surprising generalization. While we focus heavily on language because that's where LLMs shine, the same fundamental architecture can be adapted to various tasks beyond text. People are using transformer-like models for image processing, treating image patches as tokens, speech recognition, protein folding, and more. This is possible because ultimately all these different data types, whether they're words, pixels from an image, segments of audio, or amino acids, can be broken down into sequences of tokens and embedded as vectors. Once they're vectors, the transformer machinery can process them, treating them essentially as equal citizens within the same computational framework.
That is truly mind-blowing when you step back. The same underlying mathematical machinery attention, MLPs, embeddings, gradient descent, can learn to understand the nuances of a Shakespearean sonnet, the visual patterns in a cat video, or the structure of human speech, simply by changing how the data is initially tokenized and embedded. It really points towards a potentially universal architecture for learning patterns and relationships, regardless of the data modality. It's a testament to the power and flexibility of these core principles. What an incredible journey we've taken today. We started right down at the simplest level, with the humble artificial neuron, basically just a number between 0 and 1, like a tiny light bulb that lights up with activation. We saw how these neurons combine into layers, input, hidden output connected by weights, the knobs, and influenced by biases, the offsets, and how activation functions like ReLU shape their output. Then we demystified the core learning mechanism, how these networks actually get smart. It's about defining a cost function to measure how lousy they are.
Measuring the error.
And then using the iterative downhill process of gradient descent, powered by the clever backwards flow of error signals and backpropagation, to constantly tweak those weights and biases to minimize the cost, to get less lousy.
And from those fundamental building blocks, we made the big leap to transformers. We explored how they completely changed the game for language processing by ditching slow, sequential processing in favor of parallel attention mechanisms. We saw how attention lets words talk to each other through that dynamic dance of queries, keys, and values, figuring out context on the fly. We touched on multi-headed attention giving diverse perspectives and how those big MLP layers act as crucial knowledge hubs, storing the vast factual understanding that emerges purely from exposure to data during training.
And ultimately, understanding these core components from how a single neuron fires, to how attention allows words to dynamically weigh context, to how billions of parameters collectively absorb and represent knowledge is really essential for grasping the true nature and capabilities of modern AI. It demystifies it. It shows it's not magic, but rather a really sophisticated interplay of mathematical principles combined with clever engineering like residual connections, all applied at an unprecedented scale and fueled by immense amounts of data.
Indeed, it's complex, but it's understandable. And as we look forward, considering ideas like that superposition hypothesis, it really makes you wonder if these models can genuinely encode far more ideas, far more features than their literal dimensions suggest. What unarticulated depths of understanding might they actually be developing within those vast, hard-to-interpret, almost perpendicular spaces inside their parameters? It leaves you pondering the profound implications of these emergent properties, what intelligence really means in this context, and what new capabilities might be quietly unfolding within these increasingly complex digital minds. It's certainly something to keep thinking about.